What's up, everybody? I'm John Church, a product manager at Nethermind, and I'm going to be talking about the MEV infrastructure bounty. We're supporting a StarNet MEV infrastructure bounty because StarNet needs MEV infrastructure, and especially as StarNet moves towards a decentralized ecosystem. And we think that helping people get involved with some of the different bounties and building products and ideas in the MEV infrastructure space will help StarNet's ecosystem be more healthy and have healthier markets. So real quick, high level, what is MEV? It's called maximal extractable value. Originally, it was minor extractable value. This term has changed over time, but it roughly refers to the value that a miner, validator, block producer can extract from manipulating or managing or messing with the order, inclusion, exclusion of blocks and transactions within a block. MEV can be positive, MEV can be negative, and that's why this is an MEV infrastructure bounty, which is we want to help dApps and the larger ecosystem make MEV a neutral or positive force, because when MEV is properly accounted for, properly built, it becomes revenue stream for apps, and it becomes revenue stream for the larger ecosystem, and ultimately helps make markets more healthy, helps make pricing in the markets like a Kubo and others, makes pricing more accurate and aligned with other marketplaces like Binance, Coinbase, Ethereum, etc. So it's critical for supporting healthy markets, and that's what we really want to enable. Due to StarNet, currently StarNet is a first in, first out, or first come, first serve transaction order flow. So due to that, the MEV is a bit limited in terms of which is good. This is fine. It's front running, sandwich attacks, etc. are very, very hard to do, and that's great. And that's partially why we wanted to do this as a StarNet infrastructure rather than anything else. So just kind of highlighting that we want this to support healthy markets. Examples of MEV infrastructure. Solver markets like CowSwap or Uniswap X, like these are some ideas that you can use to think about, what would you like to build? So solver infrastructure examples on L1 or CowSwap, where they created a marketplace for solvers and user intent. So user intent comes in, I want to swap ETH to USDC or USDC to ETH, and then solvers go find the best routing and best pricing, and then they present that. They take that swap and then they present that to the user. So solver markets, dApp infrastructure to integrate MEV. This is something that I think CowSwap specifically created the UI and then the solver infrastructure. I think that there's opportunities in terms of creating solver infrastructure that is UI agnostic, and so you can plug into different dApps, or dApps could use that, maybe like an SDK or libraries. I think there's a lot of opportunities there. Also generating intent markets, and this is kind of an adjunct to the previous example of the dApp infrastructure to integrate MEV. Generating a marketplace where solvers can compete, where user intents come in. And then ultimately, I think exploring this space is a big opportunity. Like this is the MEV infrastructure space is wide open. There's a lot of research, a lot of thought, a lot of novel exploration around different ideas happening in the MEV infrastructure space. How do you aligning MEV to the different layers that they're on, to the dApps that they're on, to the wallets that are being used. I think that there's new and novel ideas are certainly welcome here, and especially MEV in relationship to cryptographic like ZK integration into MEV. I don't think this has been explored yet, I think that there's a lot of opportunity, like proving compute through ZK. Um, I think there's some novel thought and novel products and ideas that can happen there. Just high level requirements for judgment. To be considered, your project source code must be hosted on a repository like GitHub, must be your own work, and you must demonstrate that it's executable on StarNet testnet. So it's got to work. Your project will also be judged on the quality of the cryptography underlying the project. Basically, like how much do you use the novelty of StarkNet and ZK and what's available. Also, the quality of the implementation will be judged, and the amount of work that you've done on this during the event. And these are some resources that I think are important, and I'm just going to talk through them really quickly. The StarkNet MEV on this iSchool's StarkNet MEV repository is a list. There's a number of bot builders, bot templates, and high level information on how does StarkNet work, how is it different than L1, and so if you need some quick information on how to get there, that's a great place. Also, the Ethereum docs on MEV, which is just a high level primer on what is MEV, how does it impact L1. I included Anoma as a research resource because Anoma is doing some really interesting work in terms of intents marketplaces, which ultimately capturing intents and moving them into solver networks or searcher networks, I think, or in searcher marketplaces, I think there's a wide open space for unique products. Cairo Lang is, of course, the language of StarkNet, so you'll need to know that. And then the crash course in StarkNet is a publicly available Notion page for that we've produced to help people get up to speed on StarkNet. I think that's about a wrap. Again, I'm John Church. Best of luck out there and get those bounties.
Test. Am I on? Okay, cool. Hey, everyone. Thanks for coming this morning, bright and early. I'm Josh. I'm a software engineer and engineering manager at Nethermind. And today I'm really excited to talk about Monomer, a collaboration between Nethermind and the amazing Polymer team to bring the Cosmos SDK to the OP stack. Before we discuss what exactly that means and how it works, I'd like to just get a show of hands. Who here has would consider themselves as a smart contract developer? Like you've written Solidity or some other smart contract language. Okay, good number of you. Who here has deployed a smart contract on an L1, like Ethereum mainnet or a testnet? Testnet counts too. Okay, basically everyone who is a smart contract developer. Who here has deployed a contract on an L2, testnet or mainnet? Okay, about half the number. Okay, and then who here has deployed an L1 network or an app chain as an L2? L2, okay. Okay, actually more than I expected. But it was a different group than the smart contract developers. So the purpose of this talk and the purpose of Monomer is to really bridge that gap between the smart contract developers and the maybe infrastructure developers. Give the smart contract developers the power of amazing infrastructure and give the infrastructure devs the ability to write amazing applications. Here, let me grab the clicker. Awesome. Okay, yeah, so we'll discuss like the motivation for Monomer. We've already kind of discussed that a little bit. And then we'll go into how it actually works, what it does, how you can use it, and then finally conclude with what's next for us. So today, developers, myself included, have to choose between kind of this two ends of the spectrum. You either have to choose like security and network effects if you want to deploy your application on like an L1, on Ethereum mainnet. You get great composability. It's really easy to use. MetaMask works out of the box. You don't have to worry about all this underlying infrastructure. It's kind of like deploying in Vercel and Web 2. Everything's taken care of. It's a very smooth experience. And then on the other end of the spectrum, you have like the equivalent of deploying on-prem your own hardware in Web 2, which would be like deploying an L1 app chain. You know, it's very expensive. You have to pay your validators somehow. That includes inflating your token, which can be bad for your ecosystem, and caring a lot about things that don't have to do with the actual business logic, the actual product that you're building. But you get some benefits. It's maximally customizable. So you get great technical sovereignty on this end of the spectrum. You get great security, great network effects on this end of the spectrum. I think what's really interesting and where we should converge is somewhere in the middle of this. Maybe you can compare this to AWS and Web 2. You know, maybe I'm stretching the analogy too far. Right now, I think this means deploying something like an EVM L2. You see some chains doing this. World Chain recently announced that they're launching a separate chain. Aave has indicated that they're going that direction as well. Lens is another example. So I think deploying a custom L2 gives you some benefits of this. You inherit the security of Ethereum mainnet, as well as maintaining some technical sovereignty over how you allocate block space and how your application runs under the hood. So the main thesis of this talk is that this is kind of a false dichotomy. There's no reason why you can't have technical sovereignty and control over your application while still inheriting the security and network effects of the platform that you're building on. In this case, it'll be the OP stack and Ethereum mainnet, but I think this will apply to a lot of other ecosystems as well. Monomer focuses on Ethereum mainnet, but I think the principles that we'll discuss today apply to other chains as well. Okay, yeah, so the thesis is you don't need to choose between sovereignty and security. You can build Cosmos SDK applications on the OP stack with Monomer, and this gives you really, really nice benefits that we'll discuss toward the end of the talk. Okay, so I want to just discuss how this is actually accomplished, because it may not be immediately clear how we take something from a completely different ecosystem, Cosmos, and deploy it on like the quintessential Ethereum product, the OP stack. So who has seen a picture like this before? This is just Ethereum's high-level architecture, you know, the division between the execution and consensus layer. Raise your hands. Who's seen something like this? Okay, pretty much everyone. And even if you're not in the Ethereum ecosystem, you've probably seen something like this before because it's quite common. Most blockchain infrastructure is converging on a separation between execution and consensus. And this even exists in like Web 2 applications where you divide like the control plane and the data plane is another way to describe it. If you haven't seen something like this before at a high level, in order to run an Ethereum validator, you need at least two pieces of software. You need your consensus layer client, you need your execution layer client. They communicate using the engine API with each other, and then with other nodes communicate over some P2P network to actually add blocks to the chain. And the way this works is the consensus layer decides which blocks will come next in the chain, and the execution layer executes those blocks. Okay, and it's really nice having the separation between the consensus and execution layer because, as we'll see, Monomer actually exploits this to kind of mix and match and do creative things by replacing either the execution or consensus layer. Okay, but the really important point here is that this division exists, and the way that this, and kind of the glue that ties the execution and consensus layer together is this standardized engine API. And the engine API isn't, like the details of it aren't really important for most of this talk. The important thing is just to know that this standardized API exists. Okay, who's seen a picture like this before? Everyone's hands should go up. It was on the last slide. In the Cosmos ecosystem, you have a very similar division between the execution and consensus layers. Instead of communicating over the engine API, they communicate over the ABCI, the application blockchain interface. There's some slight differences between the engine API and ABCI that we'll discuss a little bit later, but the important thing to note is that this is almost a carbon copy of what we saw on the previous slide. So in blue, we have the cost, instead of, well, here, let me just show you. So in Ethereum, there are multiple implementations of the execution layer, multiple implementations of the consensus layer. In Cosmos, just the way things have developed, there's usually your application is developed using the Golang Cosmos SDK, and the consensus layer is comma BFT. It's just an implementation of Tendermint. In blue, we have the Cosmos SDK app, and then below we see comma BFT. But they perform similar functions to the execution and consensus layers in Ethereum. Okay, so now this is a little bit more complicated, but it's the OP stack shares a similar design to both the Ethereum and Cosmos architectures. You have the execution layer, which in this case is OP-Geth, and then you have this kind of more complicated consensus layer that actually performs the rollup functionality. And there are other components of the OP stack that I'm not showing here. You can think of this as like the essential gist of how the OP stack works. A little bit of history. So the OP stack was originally developed for Optimism specifically. Optimism is a rollup on Ethereum, and a few years ago, one of the primary selling points of Optimism, now it's more common in part due to the Optimism team's amazing work, is Ethereum equivalence. The idea was you could deploy your smart contract on Optimism and get the exact same user experience and functionality that you would get on mainnet with just lower fees. And the way they did this was by taking the execution layer client from Ethereum, making minimal modifications, like very, very few, and
Hey guys, my name is Ayush and I work as a DevRel at Nethermind, and I'm going to tell you about the Nethermind bounty and also tell you about StarNet and why StarNet is a game changer in the blockchain space and why you should explore it being in Web3. To understand why StarNet is exciting, let us first examine Ethereum's core scaling challenges. So that would be like the block size, time constraint. So with a 12-second block time and gas limit, there's a cap on how many transactions that can be processed on chain. Then comes the state growth. As more transactions modify Ethereum's global state, it becomes increasingly resource intensive for nodes to manage. Then comes the consensus overhead. In Ethereum, all full nodes must process every transaction to reach an agreement. This universal validation requirement fundamentally limits the scalability for L1. Then comes the data availability costs. Storing all transaction data on chain is really expensive, and this leads to rapid chain growth. These factors together combine to create a network congestion and high gas fees on L1, especially during peak usage of the network. This is where layer 2 solutions like StarNet come into the picture. They address these challenges in four key ways. First is increased throughput. Layer 2s process more transactions per second by moving operations off chain. Second is reduced cost. They lower fees of the transactions by batching multiple transactions into one L1 interaction. Third comes the maintained security. Layer 2s inherit Ethereum's security through cryptographic proof generation, which in case of StarNet is specifically called a validity proof. Finally, and perhaps the most exciting one, is that they enable us to do complex computation on chain. This means we can now run resource intensive operations cheaply, opening up entirely new blockchain use cases, which still needs to be explored. So StarNet as a ZK rollup takes these benefits even further. ZK stands for zero knowledge, a cryptographic method that allows one party to prove another that a statement is true without revealing any information beyond the validity of the statement itself. In StarNet's case, this means that we can prove that a batch of transactions is valid without processing each transaction individually on Ethereum. This achieves greater scalability while maintaining security, enabling a new class of blockchain applications which were previously infeasible due to cost or computational constraints on Ethereum. So StarNet brings ZK rollups to life using Starks, which is scalable transparent argument of knowledge. Here's how it works actually. So StarNet represents its entire state using a Merkle-Patricia tree, processing transactions off-chain to update this state. It then generates a Stark proof, a cryptographic guarantee that these updates are valid. This proof, along with the compact state commitment, is sent to Ethereum for verification. The beauty of this system is its efficiency. A single proof can validate thousands of transactions, which dramatically reduces the data footprint on Ethereum. This allows StarNet to achieve throughput and lower cost while inheriting Ethereum's robust security features. By moving complex computations off-chain but anchoring the results on Ethereum, StarNet opens up a new possibility for blockchain applications. It's not just about scaling existing use cases which are present on different layers already, but it's about enabling entirely new ones that were previously impractical due to cost or performance constraints. Now let us dig a little bit more on how StarNet is classified. So StarNet is classified as a type 4 ZK EVM. It means it's optimized for efficiency rather than exact Ethereum equivalence. It's like we are reimagining what's possible with blockchain computation. This approach was crucial for scaling Ethereum because it allows for greater optimization and efficiency. By moving away from the strict EVM equivalence, StarNet can leverage custom built systems that are specifically designed for generating zero knowledge proofs. The trade-off is slightly different developer experience compared to how you do things on Ethereum. However, this sacrifice in immediate familiarity enables us to push boundaries of what's possible on the blockchain. We can perform more complex computation, handle larger datasets, and create more sophisticated smart contracts in Cairo, which is the programming language for StarNet, smart contracts, all while maintaining the security guarantees of Ethereum. And this is why Type 4 is so exciting. It's not about making Ethereum faster or cheaper, but about fundamentally expanding the capabilities of blockchain technology. Let me quickly walk you through StarNet's transaction lifecycle. It's a bit technical, but understanding this process is key to appreciating StarNet's efficiency. So the first step is transaction submission. A transaction is sent to a gateway, entering the mempool with a received status. The mempool is like a waiting room for transactions, holding them until they are ready to being processed. Then comes the mempool validation step. The mempool performs initial checks like ensuring sufficient balance for fees. This is similar to Ethereum's signature checking, but StarNet adds custom validation functions for different transaction types. Then comes the step 3, which is sequencer validation. The sequencer revalidates transactions before execution, ensuring they are still valid in the current state. The fourth step is execution. Valid transactions are applied to the state, failed transactions are included as reverted. The next step would be proof generation and verification. This is where StarNet's magic happens. The prover generates a cryptographic proof for the entire block's execution, which is then verified on Ethereum L1. This process allows StarNet to batch thousands of transactions into a single proof, significantly reducing costs and increasing throughput while maintaining Ethereum's security. It is this efficient proof system that enables more complex computations possible on StarNet. One of StarNet's unique feature is its built-in account abstraction. Unlike Ethereum's EOAs, which are externally owned accounts, all accounts on StarNet are smart contracts. This enables signature abstraction, which means that you can customize how your account validates transactions. Then potential for fee abstraction, which means that we can pay gas fees in different ERC20 tokens. Then comes nonce abstraction, which helps us to send multiple transactions in parallel. So this account abstraction built-in feature in StarNet opens up possibilities for various applications like social recovery wallets or biometrically authenticated wallets for your DApp. So StarNet uses a programming language called Cairo. Now the question comes, why do we have to learn Cairo? Why a different language? So let me introduce you to the features of Cairo. It's a language which is designed specifically for creating efficient ZK proofs, which is the key to StarNet's performance. Cairo allows developers to write complex logic that can be efficiently proven, enabling complex computation that were previously infeasible on-chain. You can do all these things just by writing smart contracts in Cairo. You don't have to create any more circuits or anything like that for creating ZK proofs. Now, if we talk about how you can dive in and start learning, we have got a range of resources to suit different learning styles and experience level. First, there's an official StarNet documentation. It is your go-to place for up-to-date guides and references for anything related to StarNet. It can help you start by setting up your environment, then declaring your smart contracts, creating an account, deploying your smart contracts, and then also interacting with them. You can deep dive into the architecture section to understand how StarNet works from an architectural point of view. For our deep dive into Cairo itself, you can use the Cairo book. It's a comprehensive guide that takes you through the language step by step to create provable programs on StarNet as smart contracts, or even a standalone provable program is possible to be written in Cairo. So this would be the go-to place to learn Cairo from very basics. For people who actually like the hands-on approach for learning any language, I would suggest using Starklinks, where you can understand how smart contracts work on StarkNet by going through all these exercises and compiling them, and also seeing if things work the way you think they are working. Other than that, we also have Cairo on Exorcism, which can help you learn Cairo. For those who enjoy a more gamified experience for learning anything, Node Guardians would be the best place because they provide challenges and quests to level up your StarkNet skills. We also have a crash course on StarkNet, which is a list of various resources that you would use during your application building on StarkNet. So I would walk you through all the resources that I mentioned here. First would be the OpenRPC playground. This would help you understand what are different methods that you can call from a StarkNet node API. For example, like the StarkNet spec version, which returns the version of the StarkNet JSON RPC specification which is being used. Now the question comes, how do you create these code snippets? If that is also something which you want from us, then you can go on to the crash course page and then migrate to the StarkNet JSON RPC builder. This is where you can request for code snippets for interaction to StarkNet using StarkNet.js or StarkNet Go or StarkNet.rs. For example, I'll walk you through a request which we can create here. To get started here, I would need an API key that I can get from Voyager, which is the blockchain explorer for StarkNet. Now we can go to access StarkNet RPC, get started for free, and here you need to create your own RPC API key. I'll name it as demo. Then we can copy this API key and go back to the JSON RPC builder, this one, and paste the API key here. Now I want to call this particular function StarkNet spec version, and I can just click on send request. You can see I get a response here saying that the spec version right now is 0.7.1. You can copy code snippets from here if you're using StarkNet.js. If you're using StarkNet.go, you can migrate here. You will get all the code snippets which are required for creating applications on StarkNet. In the crash course, you can also see that we have an introduction to Juno, which is basically a Go implementation of a StarkNet full node client, which is created by Nethermind. This would allow node operators to easily and reliably support the network. You can create your own Juno instance on a system, and you can use that for putting the RPC requests that you are creating in this JSON RPC builder. Apart from that, these are the things which you can also use, like the StarkNet CLI, then StarkNet architecture documentation, which is also present in the StarkNet documentation, then the Cairo book, and this is the bridge that you can use for Ethereum to StarkNet. So basically this bridge helps you migrate your assets from Ethereum L1 to StarkNet within 3 minutes, but a migration from StarkNet to Ethereum L1 can take a maximum up to 7 hours. Then here are some links to the major dApps documentation which are present on StarkNet. ETHGlobal is the largest AMM present on StarkNet right now, and largest transaction router is Avenue. So you can use these dApp documentations to build something on top of them as well. Then here's the link for the StarkNet ecosystem. You can go to this to explore all other community driven resources that are present for StarkNet. Whether you are a beginner or an experienced dev looking to expand your blockchain skills, all these resources will help you get up to speed with StarkNet and Cairo. We have plenty of resources apart from these which are driven by community as well. But to get the link of all these resources, you can scan this QR code. Now here comes the most awaited part, the discussion about the StarkNet.anything bounty. We are offering a prize pool of $1,000 for the most innovative project that can be built on StarkNet. So StarkNet's architecture allows for some interesting capabilities that weren't feasible before on-chain. So we have some ideas of what you could build around. So things like DeFi, AI, verifiable compute, privacy, cross-chain applications, or games. But honestly, these are just suggestions. What we are really interested is in seeing what you come up with. Maybe it's something even we haven't thought of yet. That's the coolest thing about new tech, right? Sometimes the best ideas come from fresh perspectives or hackathons like ETH Online. The qualification requirement for StarNet.anything bounty are pretty simple. The project source code must be hosted on a code repository like GitHub. The code must be your own work, and you must demonstrate that your project is executable on StarNet testnet and is working fine completely there. We are not expecting you to revolutionize the blockchain overnight. We are just curious to see what kind of creative solutions you can build using StarNet's features. So give it some thought. We are excited to see what you'll create. Remember, the goal isn't to make existing applications cheaper or migrating applications from different blockchains to StarkNet. It's to imagine and build things that weren't possible before. So if you have any idea that you think could work very well on StarkNet, we would love to see it. And don't worry about being perfect or world changing. We are here to help you for whatever need you have or whatever doubts you get. So good luck, and let's push the boundaries with StarkNet.
Hello, thanks for being interested in this bounty, the ZKL Project Bounty. So in this for this project, we challenge you to build a project that combines ZK technology and machine learning. So what does this mean? This is a very open-ended task. You might consider us. I'm going to start again. I'm a bit nervous. I don't know why. I feel like I'm talking to a wall. Okay, thanks for being interested in the ZKML project. So the main task of this project is very broad. It asks you to build a project that combines ZK technology and machine learning. This is a very broad description. It is very open-ended. So the goal of this short presentation is to give you some ideas of how you can tackle this project. So you might want to start focusing on a sub-branch of ZKML. So there's several sub-branches. There's one of the sub-branches is proving correct inference of a machine learning model. This means that you prove that you execute a machine learning model that's maybe signed by a trusted authority, and then you create a proof that this model produce such an outcome on a public input, and you also prove that the model that produced this output is signed has a correct signature by this trusted authority. This is a very hot application of ZKML. It basically allows someone who ran a model to provide a very succinct proof that the model was executed correctly, and also you can prove that your model is signed by some trusted authority. So, for example, maybe the model is signed by the government, and suddenly you have a proof that is succinct, very easy to verify, and this proof says that you pass some criteria, and you're also proving that the model that the government signed this model. So you are providing a proof that the government thinks that you pass this criteria. And yeah, and there's several aspects in here. There's the succinctness, so the proof is very short. It can be very easy to verify as compared to just running the model. You may also want to explore the ZK part of ZKML for this application. Maybe you want to hide the input as well, or parts of the model. Who knows? Surprise us. There's another sub-branch of ZKML which is a bit it is a bit less explored, less developed, because it is significantly more complicated in practice to achieve than correct inference, and it is proving the correct training of a model. So there's some data set, and you want to prove that a model was trained on that data set. That's quite complicated because the training of a model is, as you know, the most expensive part of ML. So training a large language model can cost billions of dollars or millions. Yeah, so proving such a computation with on a snark looks very out of our reach right now, but it is certainly an area that is being researched, and there are certainly teams that are tackling this problem. So you might want to also take a look at this. There's another branch of ZKML called federated learning. In federated learning, there are several parties that have data and they don't want to share their data because it's private. Maybe let's think a network of hospitals. Each hospital has its own data. They don't want to share the data with the other hospitals because they just cannot legally. So, but the hospitals want to train or run some machine learning model on all this data, and they want to merge all the data together so they have a more deep data set. So federated learning aims to solve this problem because they cannot just share the databases and merge them together because of legal reasons. They would be disclosing patient information to third parties. So federated learning is a branch of machine learning or ZKML that focuses on allowing this set of parties that have their own private data set to train or run models on this set without revealing the data sets to each other. And yeah, so these are some suggestions. We strongly encourage you to think of your own projects and to surprise us with your creativity. In fact, creativity is one of the judging criteria of this bounty. We want to see. So of course, we want to see projects that deal with zero knowledge machine learning, but we will value we will have in high regard projects that are very creative, that are built upon an idea that it is surprising and interesting. So yeah, and to finish this short introduction to the bounty, let me give you some suggestions and recommendations. So it might be easy to start by looking at the problem of proving ZKML inference, rather than, for example, proving training, because as I said, proving training is a much harder problem in terms of efficiency than ZKML inference. And also there's much less research done there. However, as I said, we value creativity highly. So if you are interested in exploring the training problem, we will also be happy with that, and we will take into account that the training problem is harder than the ZKML inference. We also recommend you to try to look and use existing frameworks for ZKML or existing domain-specific languages. One way to start a project might be to look for some existing application or project and try to optimize some part of it. For example, one part I believe needs some attention in ZKML is how the floating point arithmetic is treated right now. So I think that many projects prove operations with floating point arithmetics in ways that are a bit more expensive than they could be. I think these operations could be improved with some lookup operations, for example, basically lookup operations, maybe last source decomposability, etc. So you might want to go to some existing project in ZKML and identify some part of it that's non-optimal and try to come up with a small improvement there. That would be a great way to tackle this bounty. And also, please feel free to approach us and ask us what are these pain points in ZKML that you could focus on. We will give you more examples, like the floating point arithmetic example. Yeah, so also don't be super ambitious. Like always remember that the hackathon lasts a couple of days. This can be a hard problem. Getting into a very big project might sound great, but there might not be time to do that in a couple of days. And yeah, please look at some possible useful links that we added in the description of the bounty. Good luck, and let us know any questions you may have. We will be around.